First of all, I will talk about the introduction of this project. Second, I will talk about some model setup. As the title says, I will simply explain a minimally extended Z-prime model. Then I will talk about this effective Huchan matrix using a mixing formalism to diagonalize the mixing mass matrix, fermion mass matrix. Then I will talk about this Z-prime boson interactions with the vectorlike family. And then I will explore the lepton sector phenomenology, and then we will talk about the quark sector phenomenology. And lastly, I will talk about the muon g-2 with scalar exchange and the W mass anomaly, as well as the oblique parameters TSU. So then I will conclude. Okay, let me start. Oh, sorry. It doesn't go. Sorry, I just go manually. Okay, so let me start. So here our main motivation started from this considering anomalies, both anomalies simultaneously. So considering the muon and electron g-2 anomalies simultaneously in search for new physics has been an interesting study. Actually, one of our projects also focused on to explain both anomalies simultaneously. So based on the group K and this experiment at that time in 2018, it gives about the 3.3 sigma standard model deviation, whereas the electron gives minus 2.4 sigma the standard model deviation. So this maybe we thought we were able to find some new physics by considering these two anomalies simultaneously. But this situation changed dramatically as in 2020 because there were renewed results for both anomalies. So in 2020, by the Fermi lab, we got the renewed muon g-2 result with 4.2 sigma standard model deviation, whereas the electron gets less important because it gets reduced the standard model deviation, which is 1.6 sigma. So here, what they tell us is that the standard model deviation difference of its anomaly between its previous experimental result and renewed one tells that the muon g-2 gets more important, whereas the electron g-2 gets less important in search for new physics. Instead of the electron g-2, it can be more interesting to connect the muon g-2 with the B anomaly because B anomaly still reports 2 or 3 sigmas. So here our main goal in this project is to compound whether the muon g-2 with 4.2 sigma and B anomaly with 2-3 sigma can be explained simultaneously under all the accessible standard model constraints. So the main tool will be used is a massive gauge boson Z-prime, which is resulted from a broken muon prime local symmetry will be used for the analysis, and the observable which will be considered as follows. In the standard model lepton sector, we will consider muon g-2, neutrino trident process, and the charge lepton level violation constraint tau to mu gamma and tau to 3 mu. And the standard model quark sector, we will consider IQ anomaly, gas meson oscillation, collider constraint, and the CK mixing matrix. And finally, we will consider also the electroweak precision data corresponding to the oblique TSU parameters, as well as the W meson anomaly and the 3-level vacuum stability of the scalar potential. So we move to the next chapter. So I will talk about our model frames. So our model is extended by this, first of all, a complete vector-like family, one complete vector-like family, and then one standard model like doublet Higgs, the HD, which is the down-type Higgs, and one singlet flavor. And then the gauge symmetry is extended by the muon prime local. So after this muon prime symmetry is broken, it gives rise to a massive neutral Z-prime gauge boson. So this is standard model part. This is the complete vector-like part, one singlet flavor, and one down-type Higgs. HU is generally considered as the standard model Higgs, and then the muon prime gauge symmetry. And so this a minimally extended Z-prime model is also features the type 2 Higgs doublet model, which means the up-type Higgs coupled to the up-type box, whereas the down-type Higgs couples the down-type box and the charge leptons. So, and our doublet Higgs elements read like this ways. So both developed its fabs. Similarly, the singlet flavor has also its fabs. So we have 3 scalars in this model, and the vector PU and D meets the condition. This is the well-known condition, and our model also respects this condition. And in this BSL model, we generally consider the uptype Higgs PU to be quite close to the standard model Higgs level 246 GB, whereas the downtype Higgs level is said to be quite close to the big bang mass. So similarly, the big Cox Yucca constant is also very close to 1 in this BSL model. So the renormalizable interactions of the Cox sector in this BSL model are given by, and the renormalizable interactions give rise to this effective diagrams for Cox sectors. The above two are for the up Cox sector, whereas the below two diagrams for the down type Cox sectors. So here, as you can see, one of them is mediated by the singlet. So this small letter means the singlet particles, and this capital means the doublets. So one of the uptype Cox is mediated by the singlet vectorlike Cox, whereas the other is mediated by the doublet Cox. So here, by introducing one complete vectorlike family, we can provide two seesaw operators, the left and the right, which means two of the three whole standard model generations to get massive. So actually one of our standard model generation remain massless, whereas two of them becomes massive. So if we want to make the first generation massive, we need to introduce one more vector-like family. But in order to keep this BSL model economical as much as possible, we will keep to only the one complete vector-like family while making the second and third generation of the standard model particles massive. So that's the reason why our constraint consists of only the second and third standard model generation particles. Similarly, the same mechanism can be applied to the down-type Cox sectors. So one of them is made by the down-type singlet and the down-type doublet. We also keep this same mechanism to the charge lepton sectors. So you can see this is also one of the charge lepton singlet and the doublet charge lepton mass. And then for the neutrinos, we call this is a type 1B seesaw mechanism, which means if you take a look at this external legs, you can see one of them is the up-type Higgs, whereas the other is down-type Higgs, which is not allowed by the conventional seesaw mechanism because both of them are same as just a standard model Higgs. But since our model is not allowed due to the assigned muon prime charge, instead this type of seesaw mechanism is possible. So we call this is a type 1B seesaw mechanism. And so we want to explain the neutrino method via this mechanism, and using the different pairs of this one and different the vertex, we can lower the predicted right-hand mass of right-hand neutrinos up to TB scales, defining this vector and this constant. So let me move to the effective Yucca matrix using a mixing formalism. So in our model, if we consider the whole the fermions, our model features like this one. Here, there are two important features. The first is the upper left 3 times 3 block means the standard model fermions remain massless without further extension due to the assigned muon prime charge. And so maybe if you take a look at this left-hand, the second fermions, maybe this proceed and meet some here, and then goes straight here, meet some vector-like mass, and goes here, and some met here, and then turn right. So in this way, you can explain this standard model fermion method effectively. So it is possible to implement the standard model hierarchy as there are 3 different mass scales. So actually, the reason why we consider this mass matrix is one more reason is to relax the strong standard model hierarchy, because in this way, one of the Yucca constants is shifted by the other 2 moderate Yucca constants, as well as the one heavy vector-like mass. So the main reason for this mass matrix is to relax the strong standard model hierarchy. So, but this is not our starting point. Maybe we want to rotate this mass matrix as much as possible to implement the standard model hierarchy dynamically. So this is our starting point. So by rotating some fields,
could you stop a little bit?
Oh, sure.
What are the symmetries of the model? Is this a 3 doublet sort of model or what? I mean, what are the symmetries? I mean, let's go to put a little bit sort of back, to have the model very well explained, because otherwise it's going to be difficult to follow. What are the symmetries of your model?
Here, the extended symmetry is just the Yuan prime, the local symmetry.
So it's two Higgs doublet model.
Yes, yes, right. Actually, we call this is a minimally extended Z prime model, but actually this model is more close to this type 2x doublet model. And then the gauge symmetry is extended by only this Yuan prime local symmetry.
And where does the C prime comes from? Because you see, it's not the other. It's not a gauge symmetry. So where does the C prime come from?
No, this is the gauge symmetry.
D1 is a gauge symmetry?
Yes, the Yuan prime gauge symmetry. So after this gauge symmetry is broken, the massive Z prime appears.
You mentioned that it is a gauge symmetry.
Yes, but at that time I told that this is local symmetry. I equate the local to be the gauge.
Okay, thank you.
You're welcome. So I will proceed. So this fully rotated mathematics is our starting point. And here I like to emphasize one feature that this is there's no any assumption from this one to this one, because while rotating this psi 1L and psi 2L, we can banish one of this, for example, this terms. So in that way, we can, without loss of generality, can move from this initial mathematics to the fully rotated mathematics. So I want to emphasize that there's no any assumption while defining these ones. So under our charge assignment, this can be accessed without any assumptions. So this is our starting point, and here I want to simply replace this Huchan terms by a simple math parameters, and then switch this fourth column and the fifth column to locate the heavy vector-like message on the diagonal positions, as you can see here. So this is our starting point, and then this can be diagonalized. So for the up-type sector and the down-type sector, we approach in the same way. But here there is one important difference between the up-type mathematics and this down-type mathematics, because Charles lepton sector we were able to maximally. So as you can see, this the Charles lepton mathematics has the exactly same form of this up-type Higgs mathematics, whereas down-type Higgs has one additional this Huchan terms, because this term cannot be banished, because here in the up sector we have already used the rotation between this Q1L and the Q2L fields. So in that way we already fixed the one mixing angle between these two. So by banishing these terms, but this mixing angle is already fixed in the down-type up sector. So this term cannot be banished. So this term should be survived. And what this means is we can have all the mixing between the down-type three standard model fermions. Therefore, we can lead to the prediction for the CK mixing matrix. So here, the up-type sector, we have only 2-3 mixing angle, whereas for the down-type sector, we can have all the mixing between the 3 standard model generations. So in order to implement this standard model hierarchy dynamically, we rotated this the mathematics maximally, and the fully rotated mathematics give rise to two fermion seesaw operators, as I told you, with one complete vector-like family. And we have defined the SU2 conserving and violating mixings, which will be important in exploring the standard model efficiencies. So here, what I'm saying is, conserving is mixing defined in the same multiplexure. For example, if I rotate this Q2L and the Q3L, this 2-3 mixing angle would be a conserving. Here, if we mix this capital Q2L with this small D4L, this would be some violating mixing, and this will be some crucial part of the causing to standard model the jet level the neutral content. But this is not out of interest in this work quite a lot. So simply I will remind you of what these are. So the presence of M1 body in the down-type mathematics allows all mixings among the down-type Cox, even though the thick quark remains massless in this PSM model, so leading to a prediction for the CK mixing matrix. So this interaction
thick quark is the only massless?
In our model, the only first generation remains massless. charge lepton and the uptype quark and downtype quarks, all of the pulse generation remains massless. Sorry?
But that's not very good phenomenologically.
Yes, I understand. But now the pulse generations is here we can systemically make them to be massive by introducing one more vector-like family. But for the reason that we want to make our analysis as economical as possible, we just regard the pulse generation as a massless particle. But we can make them massive by introducing one more vector-like family. But it will definitely make our analysis much more complicated because we need to introduce much more pre-parameters. Does it is an answer for your question?
Okay.
Okay, so let me move to the next part. So this interaction mixing matrix can be diagonalized in this way using the left and the right in the mixing matrix. Similarly, the up sector and the down type sectors. So all of the pulse generations remains massless in this BSM model. So you can see we can diagonalize the second and third generation of this standard fermions while predicting mass scale of vector-like doublet and the singlet, the charge lepton, up-type box and the down-type box. So this one, and as I told you, this numerical mixing matrix can be separated by the S is conserving and the violating mixing. Blue is conserving and the red is the violating. But this is not very relevant to this project, so I will skip this point. Okay, so I will move to the J-prime boson interactions with the vector-like family. So let me start. Here, the J-prime interactions with the both vector-like fermions in this flavor basis is like this. We can write down this J-prime interactions in the flavor basis in this way, and then these are the charge assignment defined in our minimally extended J-prime model setup, so we can have this DQ. And here, the important feature of this defined these are the standard model fermions do not interact with the J-prime gauge boson in the flavor basis. However, it starts to have interactions with the standard model fermions via mixing in the physical basis. So after we rotate these, it starts to have the J-prime interactions with the standard model fermions. So this feature is known as the fermiophobic J-prime gauge bosons. So the J-prime interactions in the physical basis rate. So after you rotate these ones, you can start to implement the J-prime interactions with the standard model gauge bosons. And the rotated D primes are defined in this way. So maybe we need to we need to build all of the charge lepton and the quark sector mass matrix to derive this J-prime interactions to the charge lepton or quarks. But for the neutrinos, instead of building the complete mass matrix, we want to analytically derive only one interaction because this interaction will be used for the constraint neutrino trident. So the systemic analytically we can derive via using the type 1b seesaw mechanism I told you. So here I just cited our derived result. But if you are interested in how to derive this result, I recommend you to refer to our latest paper, which we introduced how this value is derived. So we are ready to go to explore the lepton sector phenomenology because we have defined all the mass matrix and the coupling constant. So we start from the lepton sector phenomenology. Here, before we start, I want to clarify one feature of this BSM model. So in this BSM model, one complete vector-like family can provide two seesaw operators, which means two of the whole standard model generations can be massive. So as I emphasized, so in this section, what we want to investigate by analyzing the lepton sector observers is two features. The first is a possible highest order of the J-prime coupling constant GX, because this GX is related to the quark sector analysis as well as the scalar mediated or the gauge mediated observables, which are muon g-2, oblique parameters, and W mass anomaly. So the determining how the high it can be is very important, and we want to achieve that by investigating these lepton sector observables. So, and the second one we want to achieve in this lepton sector phenomenology is the scan the range of the coupling constant, the G mu mu L and the Z prime to mu mu left-handed and the right-handed, and the summing over these ones. So this will be used for analyzing IK anomaly. So this will be used to determine Z prime mass range from the IK anomaly, and this summation will be used for to derive Z prime mass from the neutrino trident production constraint. So we can start from the muon G mass. First of all, we consider this muon G mass at one loop level mediated by this Z prime. So here the cross notation is the helicity flip process, and it can arise between the sum of the legs. First of all, external legs, and then maybe in the internal legs. And as you can see, this the analytic precision takes these forms, and here the most dominant terms comes from this one, which has this enhancement vector over this heavy vector-like method divided by this muon method, because in our model, generally this vector-like doublet or single method is much heavier than the muon method. So generally, these two terms are most dominant. So and then where the f and g are the loop functions defined in this loop. So f and g, and the x is the ratio between the mass of the mass running loop in this loop mass scale and divided by the Z prime mass. And the most recent experimental bound for the muon G mass at 1 sigma is given by the Fermion lab, which is giving rise to 4.2 sigma standard model deviations. And then we can also access to this tau to mu gamma, the charge level violation, tau to mu gamma decay. So if you substitute the one of the external legs, for example, the left external leg by the tau, then we can have this tau to mu gamma. So I counted all polarized the diagrams, and then its analytic expression takes this form. And as you can guess, temperaturely, the terms having enhancement vectors are the more dominant. So this is the left-handed, and this is right-handed. And it's the experimental branching ratio tau to mu gamma give rise to this value, which has logarithmically order of -7.4. And then nextly, we consider this also the charge of level violation tau to 3 mu decay, because this decay is accessible via 3 level in this model. So here, similarly, I counted all the polarized bases, and then derived some analytic expression of these branching ratios, and then its experimental value has a similar order of -7.7 logarithmically. And then the final lepton sector observable we will consider is the neutrino trident production. And then this neutrino trident production can be explained via this effective operators after integrating out the degrees of freedom of this Z prime gauge bosons. So we get to have this one, and this can be further simplified to these forms. So maybe we can make use of the distance to determine the Z prime message. And here we already determined this Z prime to nu mu nu interaction in our previous sections. So maybe here what we need to determine is only the summation between this left-handed Z prime mu mu and the right-handed Z prime mu mu. So this is how we set up our free parameters. So here in our model, the down-type Higgs value is very close to the down-type equal the message. So we generally in our model this has a numerical value of 5. So we set up this value to be some this range within this Huchan constants part of the limit. And this P5 and the vector-like method is just free parameters. There's no strong way of constraining these free parameters. So we simply put this value as a pure free parameters. And here what we constrain first is the standard model muon and the tau method, as well as the 2-3 mixed angle. So in our model, our predicted muon method should be located between the 1 minus 0.1 the experimental muon method and plus the 0.1 the experimental muon method. Similarly, we also implemented the same constraint to the tau method, and we considered this 2-3 mixing angle, charge reluctant 2-3 mixing angle should be less than the 0.2. And we generally consider the uptight Higgs wave is very close to 246 GeV, whereas PD is said to be quite close to the Big Bang method by fixing the tangent beta is 50. And as I told you later, this is also the very preferred choice to explain muon G-2 with the scalar exchange. I will talk about that later. And so that the bottom of Yuka is very close to 1. And the lower J-prime method, here this is the lower J-prime method is set to avoid the constraint, these ones coming from the decay process, the PP to the J-prime to fermion. So to avoid this constraint, we set the lower mass limit of J-prime to be the 75 and we want to scan from 75 to 3T. So we take the highest order of J-prime coupling constant GX to be order of unity. This is assumed. This is an assumption, but I will talk about this unity is not ruled out by the electron sector observer. So this is our first numerical scanned result. So here, if you take a look at this x-axis, this is the double-lab vector-like charge rectangles, whereas the y-axis tells the single-lab vector-like charge rectangles, and this darker blue region is means this double-lab and the single-lab charge vector-like lepton message are excluded by 200 GeV from a reference, and this soft blue region means this is excluded by the 790 GeV by the CMS experimental result. Therefore, the only benchmark points living in this white region are only the survived benchmark points. And here, the first plot tells is the lepton sector observer cannot constrain this assumed this parameter set of error. So the lepton sector cannot constrain the J-prime method, the error. This is the first plot tells, and this is the x and y axis, all of them are same, but I put only the different quantities in the legend. So here, if you take a look at this one, this is the muon G-2 mediated by the J-primes. So here, this coloring is consistent with some of these regions, and actually I confirmed this. The benchmark pointers order is about 10 to minus 11. Most of them are the 11. Some of them are 10 to minus 10, but most of them gives the 10 to minus 11 with all negative signs. This is also a very promising picture because in our previous research, we saw that sometimes this muon G-2 mediated by the J-prime can be positive or negative. So it is not fixed by negative, but after we defined the J-prime contributions in this space model, actually I learned that this become only negative with the order of 10 to minus 11, so which is quite negligible. So here, this is tau to 3 mu, and I told you the experimental boundary is about minus 7.4, but most of them survive. So very a few of them is excluded by the tau to mu gamma experimental constraint, which means the J-prime coupling constant GX, we set it to be order of unity, but it is not ruled out by this experimental constraint. Lastly, I will see this tau to 3 mu decay, and as you see, all of them are none of them is excluded by its experimental constraint. So logarithmically, it gives minus 7.7. So our benchmark points predict all of them are safe for this tau to 3 mu decay. So very few of them is removed from this tau to mu gamma constraint. So after removing the excluded benchmark points, then we get to have this form. So here, we can what we can conclude in this lepton sector phenomenology is the assumed highest order of GX unity is not ruled out by the lepton sector observers. This is the first feature we found. The next feature is it is possible to scan the numerical range of the J-prime left-handed or right-handed muon pair from the survived.
Those questions here.
Yeah, sure.
One of them is, why didn't you consider the G-2 of the electron? I mean, why only the muon?
He told us.
I told you that we cannot make the first generation of snowball fermions to be massive. So here we didn't consider the electron G-2, and I will clarify that at the very beginning. I will consider the muon G-2. here I didn't say the electron g-2 because in this model, the electron remains massless.
Well, should be there, but I don't understand. The other question is the following. The other question I have is the following.
Yes, if in order to investigate the electron g-2, actually, I think this is a very important idea. It is possible after we assign all the standard fermions to be massive, then we can make some electron g-2 prediction.
The other question I have is the following. If you want to constrain also the C prime, I think it's going to be important also in electron positron going to muon anti-muon, which is very well known. The cross section for that. Why don't you consider that also?
Because this model is a very effective approach. So as you told, we can investigate the observers consisting of first standard model generations. In order to do that, we need to introduce one more vector-like families, which means this mathematics must be 7 times 7 in order to make this first generation to be massive. Because this is our starting point. So in order to make the first generation, we need to introduce much more the pre-parameters, and it will make our analysis much less trustable. So in order to avoid that, we fix the number of vector-like family to be only 1, and then with the number of only 1 complete vector-like family, we can make only second and third generation to be massive. And by doing so, we can access to the first the observer consisting of first standard model generations.
Okay, I didn't follow very well, but okay.
Okay, so just a moment. Okay, so here it is possible to scan the numerical range of the Z prime to left-handed muon and the right-handed muon pair from the survived benchmark point, and the scanned value is like this way, runs from 10 to minus 6 to 10 to minus 3. And right-handed the Z prime to muon pair runs from 10 to minus 2 to 10 to minus 4. But this is has a negative signs. And the summing is runs from this one, negative to 10 to minus 2 to positive 10 to minus 3. And using the derived result of this summation, it is possible to determine the Z prime mass range as given in the following table. So if we take we will take each boundary value of this one and this one, and using each one, we can derive these 2 conditions, and the combining both results, we can conclude the Z prime mass should be heavier than the 0.920 GeV in the neutrino trident constraint. This is what we got in the lepton sector observers, and then we move on to the Hawk sector phenomenology. So the first observer we will consider is the IK anomaly. So the IK anomaly and the BS decay, which is connected to the IK anomaly, the crossing symmetry, can be explained by the effective Ball fermion operator after integrating out the Z prime mass as in the neutrino trident. So this Wilson coefficient, left-handed Wilson coefficient features these forms, and right-handed Wilson coefficient features these forms. So here, what we need to is this Z prime left-handed to PS quark pairs, because we already find these values from the lepton sector observers. So here, what we want to numerically derive is the Z prime to the PS quark pairs, left-handed pair, and we will also do the right-handed PS quark pair, because which is required for the PS measurement oscillations. So here the relevant Feynman diagrams contributing to the IK anomaly and the PS mu decay is given like this way. So this is the IK anomaly mediated by the Z prime at 3 level. This is PS mu also mediated by the Z prime. So we can start from here. The effective interaction in equation 27 can be rewritten in terms of the vector and extra vector effective operators. So this Lagrangian can be rewritten in terms of the Hamiltonian. So in this way, and then maybe the Wilson coefficient is related to this delta C9 and the delta C10, this coefficient, and this n is a normalization vector. And So as you can see here, the Wilson coefficient can be linearly expanded in terms of this the coefficient. So, and then the error of the coefficient delta C910 are investigated for two cases. One of them is known as the theoretically clean peak, which means the IK anomaly and the PSM mu can be explained simultaneously without the size of the theoretical uncertainty. Whereas there is one more case which is a global peak, which is an experimental result, but there exists the size of the theoretical uncertainty. And if you take a look at here, both of them, then maybe you can say that considering the constraints coming from the theoretical clean peak, this left-handed Wilson coefficient runs from this value to this one, and so this is the global peak, and this value runs from this one. So there looks like they are consistent to each other very well. So maybe we can find some overlap reason between this theoretically clean peak and the global for the left-handed Wilson coefficient. Whereas if you take a look at this right-handed Wilson coefficient, its behavior is quite different, because in the theoretically clean peak, this negative contribution is much more dominant compared to the passive contribution, because which is very close to zero, whereas this has a much larger value to the negative side. Whereas if you take a look at this global peak, this negative contribution is much smaller than its passive contribution. So which means if we take a look, consider this right-handed Wilson coefficient from both sides, looks like this is a reason why many researchers consider this right-handed, there's no right-handed Wilson coefficient contribution to the IK anomaly, because this is the negative dominant, this is the passive dominant. We will check this numerically in our numerical scans. And then the next observable we will consider is the best measure mixing oscillations, and the effective best measure oscillation takes this form, and this the coefficient 3 can be written like this way, and we counted all polarized bases, which is mediated by the Z prime at 3 levels. And for the PS measure oscillation, we can turn to 3 constraints, 2 which are theoretical, and finally is the experimental. So first of all, the theoretical constraint for the PS measure oscillation is the lattice simulation, which gives rise to this constraint. And the other theoretical constraint, which is combined by this lattice simulation with this sum rule event. So maybe it gives some looser constraint compared to this one. So, and finally, we will also consider we will derive this constraint from the experimental constraint directly. And this is our numerical, our analytic prediction for the PS measure oscillation U-physics effect. And this effect should be located between the error bars, minus error bar and the plus error bar. So our prediction should be located this one. We will consider all these 3 constraints for the PS measure oscillation. And we move to the collider experimental constraints. So regarding the light Z prime method, it can be constrained by the decay process PP to Z prime to fermion, as I told you in the lepton sector, to avoid this constraint. And the Z prime method can be also further constrained by LHC, the dimensional resonance measurement, which is PP to Z prime to mu, which are this processor, and using the narrow width approximation.
I have another question.
Sure. Sorry, are you talking to me?
Professor Ivan, please go ahead with the question. Professor Ivan, we don't listen you for your question.
We do not hear.
Excuse me.
Continue.
It seems he's having some internet connection problem. Sometimes internet here is unstable.
Then should we wait for?
You continue, and then when Professor Ivan connects, he will ask the question.
Okay. Then I will proceed. So using the narrow width approximation, the cross-section for the decay process is given for any BB because the BB is the most dominant channel for decay channel over the Z prime. So maybe it can be analyzed using this narrow width approximation. So consider the path of decay channel takes the muon neutrino pair and the BB and the SB and the TT. So the decay width over the vector takes this form, and then given that the dimension resonance data from Atlas gives the experimental bound of Z prime method, which is runs from 150 to 5 TeV. So this will be used as one of our constraints to constrain our Z prime method. And then finally, final observable we'll consider in the Fox sector is the CK mixing matrix. So here we can make a prediction for the CK mixing matrix. But as I told you, in the up-type Fox sector, we can only have the 2-3 mixing, and we can have all the mixing in the down-type Fox sector. Therefore, our CK prediction is not the complete one. Instead, our CK prediction is some effective approach. So please keep that in mind. And then, since if we count all this left-handed Fox doublets, including the vector-like Fox, all of them are the doublets, whereas one of them is a singlet. So due to this factor, we consider this singlet left-handed uptype Fox doesn't couple to this W current. Therefore, now you can say why there is only 1, 1, 1, 1. Here the final term is the 0 because the singlet doesn't couple to the W in this BSM model. Therefore, if we consider this 5 times 5 mass matrix, which is given by this CK mix matrix, our CK prediction doesn't feature unitarity. So the non-unitarity data can be defined in this way: the 1 minus the UD scale, US scale, and the UV scale. And we can explain this non-unitarity in a very natural way without imposing any other assumption or something like that. So this is one of the fully fitted CKM prediction. So what we found via the numerical scale in the previous work is the non-unitarity delta of the CKM mixing matrix is quite small, which has an order of 10 to minus 4, and compared to its experimental upper limit, which has an order of.
I'm sorry, I was going to ask you a question, but somehow I lost the connection completely here.
It's okay. Yes, we wait to you, but. It's okay.
Yeah.
So let's go back to this part.
Well, the question is the following. I mean, you are considering only the C prime.
Yes.
Well, there are many things that in their model, they should have other particles also contributing. Why is only the C prime that contributes to everything? Even in the case of the decays of these B's and D's, there should be other particles that contribute, even some Higgs-like particles, and Higgs should contribute to some of the processes. Why are you considering only the C prime?
The reason why we consider Z prime is as and I mentioned in our in this title. So just a moment. So the main motivation is can the muon anomalies magnetic moment and the P anomaly be simultaneously explained in a minimally extended Z prime model. So the Z prime is our main target in this work.
Your model doesn't contain any other particles that can contribute? I mean,
No. Definitely, we have the additional contributions led by this down-type Higgs, the additional Higgs or something like that, and it will be covered in this chapter 7 muon with the scalar exchange. But here, up to this chapter 6, what we want to talk about is we want to see whether the muon g-2 and the P anomaly can be simultaneously explained in a Z prime. That is the reason why we focus on Z prime most.
Okay, thank you.
Okay, so let me move back to the place. Just a moment. Okay, so I will talk about from here. It's okay. Yes. So non-unitarity, the predicted non-unitarity is quite small compared to its experimental upper limit. So maybe this is not also ruled out by the CKM non-unitarity experimental constraint. So the most fitted CKM prediction, we take this one, and as emphasized we don't have the uptime 1, 2, and 1, 3 mixing angle. Therefore, our secant prediction is an effective approach. So that is the reason why our secant, the fitted chi-square function has a very large value, because 1, 2, 1, we don't have 1, 2, 1, 3 uptime mixing. So it gives rise to this our secant prediction, and we consider our attention up to this 3 times 3 mathematics, upper mathematics. We can compare our numerical prediction to the experimental secant prediction without non-unitarity. The secant prediction without non-unitarity is given by these 2 references, and then we compare our numerical result, and then notice that in our prediction, this 1, 3, 2, 3, and the 3, 1, and the 3, 2 cannot be beaten by a small difference. But notice that we have all the downtime mixing angles, 1, 2, 1, 3, 2, 3, whereas we only have 2, 3 uptime Higgs in this data model. So our prediction is, even though the secant prediction is an effective approach, it fits quite well to the experimental result. So here I will talk about some numerical analysis I did. So it's a numerical, the parameter setup is exactly same as the Charles lepton sector. So by converging the chi-square functions to some point. So here I don't want to repeat the same process. Instead, I want to show you how the derived result. So here if you take a look at all the plots, here the x-axis is the doublet of type vectorlike box, whereas the y-axis is the singlet of type box. And similarly, this is a doublet down type vectorlike box, and this is a singlet vectorlike down type box. And then I just changed some x here, so the doublet of type box, and this is just the doublet down type box. This is a doublet singlet vectorlike box, and this is a double singlet vectorlike down type box. So here, if you take a look at all the plots, they show no correlations. So instead, they just tell you the possible range of each the quark message. But this third one gives the very strong correlations. Actually, this doublet vectorlike uptype box is its method is proportional to the downtype box method, and this plays a very crucial role in suppressing the oblique parameters, because if the doublet vectorlike box contribute to the oblique parameters, and if their method size difference is sizable, it will cause the maximal violation of the custodial symmetry, which becomes very problematic in the oblique parameters. Therefore, in this PSA model, we can explain this degenerate the uptype doublet vectorlike method and the downtime method. This is a very pleasing result for the oblique parameters. And here the given numerical method range of each vectorlike box is given like this way. So the the vectorlike uptype box runs from 850 to 2250, and similar like this way. And the most updated vectorlike quark method constraints come from the Atlas experiments, which is given by this way. So this is a doublet and the singlet, and similarly doublet and the singlet, and the uptype doublet is should be heavier than the 1.6 TeV, and the downtype is 1.42 TeV. And very pleased, fortunately, this quark method, numerical quark method, the scanned methods are free from this constraint, which means also the quark sector is not ruled out by this Atlas experimental constraint. So we can scan a numerical range of the coupling constant for the interaction shape from the QQ from the survived benchmark points as in the restaurant sectors. So for here I also included the muon, the shape prime to muon, left-handed muon and the right-handed muons for convenience. And then this is scanned left-handed PS shape prime to PS and the right-handed PS, and this is same. So here this PSL and the PSI, these two are added newly. So this one of them runs from 10 to minus 2 to similar 10 to minus 2. It's very their magnitude is very the same, but with different signs. Similarly, right-handed PS is somewhat much more suppressed compared to its left-handed interactions. So from this using this numerically scanned this coupling constant, we can derive the Z prime method ranges from the diverse observables because I already showed you the constraint for neutrino trident, IK anomaly with the Wilson coefficient and the base measure oscillations. And using the constraint, we can derive mass range of the Z primes. So we start from this one. So let's take a look at this neutrino trident. So MZ prime is as I already showed you, this is should be heavier than the 0.920 GeV. But this is actually quite negligible compared to other constraints. So maybe it may not be very important. And then we can see the IK anomaly. And here I already explained what the theoretically clean bit and the global bit. But here I separated these each the same bit by two more cases. One of them is the constrained by both the CMS experimental result and the tau to mu gamma, and one of them is constrained by only tau to mu gamma. And the reason why I separated by these two cases is, first of all, I want to show you how this Z-prime method range is affected by these two cases. So I will simply remind you of these two experimental constraints. Just a moment, my computer is sometimes slow. Oh, sorry. Yes, here the CMS experimental result is this soft blue region, which is which tells you the 790 GeV. This is the CMS experimental constraint, and then the tau mu gamma constraint is this one, which is excluded by minus 7.4 logarithmically. So here we implemented the experimental conditions, tau to mu gamma and the CMS experimental constraint. So first of all, using each the boundary value of this derived coupling constant, we derived this Z-prime message. First of all, we consider this theoretically clean bit with both the two experimental constraints, and then I got this Z-prime is from 220 to 245, whereas for this right-handed Wilson coefficients gives much heavier than the left-handed, so which is 2600 GeV, should be heavier than these values. Similarly, when I consider tau to mu gamma experimental constant alone, the right-handed Wilson coefficient has no significant change compared to this previous one. Instead, left-handed Wilson coefficient, this becomes much heavier compared to this one. And so as you can see, the CMS experimental constraint play a role of suppressing the right-handed muon coupling constant. Therefore, this is the very reasonable mass range derived from by considering this experimental concept alone. And then this is experimental constraint, global bit, and we consider both the constraints, and then it gives the Z-prime runs from 200 to 220, and then the right-handed Wilson coefficient gives much heavier than the 1 TeV, and similarly the global bit. So and then I also derived this method found from the PS measure oscillations, and then gives this is the lattice simulation and the lattice simulation plus some rule, and this is our own experimental result, and which gives much heavier than the IK anomaly. So here what we can conclude is, first of all, the IK anomaly is very likely to be explained by only left-handed interactions, because if you take a look at this plot, there's no any overlap reason between the left-handed Wilson coefficient and the right-handed Wilson coefficient. Because we conclude, our conclusion is the IK anomaly is very likely to be explained by only left-handed interactions. And then the IK anomaly and the muon G-2 cannot be explained by the same new physics Z-prime, because as I told you, the muon G-2 made by the Z-prime gives only negative contributions with the order of 10 to minus 11. So, and we will discuss that the muon G-2 can be explained via the scalar exchange at one loop level of the 2 sigma over its experimental constraint by connecting the IK anomaly, the to be more specific, the IK anomaly source Z prime via the scalar potential. So, and the Z prime for the IK anomaly, yes, I told you, Z prime for the IK anomaly and the non-standard model scalars for the muon G-2 can be connected via the scalar potential in the theoretically interesting Z prime reason, which means the global field with the tau to mu constant alone only. So here, what I'm saying is, we consider this mass bound to be the theoretically interesting Z prime reason because this mass range is the only possible place where the muon G-2 mediated by non-standard model scalars can be connected to the Z prime for the IK anomaly via the scalar potential. So especially recall that this is the theoretically interesting Z prime region, but this region is actually less interesting because all this experimental concept isn't reflected. So, but anyway, we call this is a theoretically interesting Z prime region. So the time is okay. I think I already passed. Antonio, the time is enough.
It's fine. Just
okay. Thank you.
You can continue. Just
okay. Thank you. So we can start from the exploring the muon G-2 with scalar exchange and the W mass anomaly. So unlike the previous chapters, here we have mainly focus on the Z prime physics, but instead in this time we consider the non-standard model scalar contributions to the muon G-2 and the W mass anomaly. So let's start from here. In this BSM model, the Higgs alignments in this interaction-based service, the uptype Higgs takes this form, downtype Higgs, and the singlet lepton takes this form, and all of them have their paths, which means they break the each gauge symmetry. So the scalar potential takes this form. So this is allowed in this BSM model. So we have the A quantic coupling constant and the 3 dimensional method parameters, which must be negative to implement the depth. So the minimization conditions of the scalar potential give rise to these ones. And then we consider from the CP even mass matrix scared order and the charge mass matrix scared. And then so this is our the CP even mass matrix scared. And then in order to make our analysis for the scalar sector much simpler, we will apply the decoupling limit to this CP even scalar mass matrix, which means this is a mass scared over the standard model Higgs, and this would be some non-standard model scalars. For let's say the CP even Higgs H1, which is lighter than this heavier than the other CP even scalar. So this is H1 scale, this would be H2 scale. And by applying this decoupling limit, our standard model Higgs doesn't couple to any H1 or H2. So in other words, we want to banish this 1, 2, 1, 3, 2, 1, 2, 3 the interactions by implementing this the decoupling limits, which is defined between two decoupling constants with the suitable coefficient. So in this way, the actual our numerical this mass matrix takes 1, 1 and 2, 2, 3, 3, 2, and 3, 3. So anything 1, 2, 1, 3, 2, 1, 2, 2, 1, 3, 1. So and the CP order mass matrix in the interaction base takes this form, and this 1, 1 entry become a Goldstone version for the standard model Z-gauge version, whereas this 3, 3 would be another Goldstone version for the Z-prime gauge version. So remaining only one non-standard model CP order scalars. So because this would be A1 in the order base, and it can be diagonalized in this way. The CP even is also can be diagonalized in this way. So similarly, in the charge mass matrix scaled, we have one Goldstone version for the standard model W version, and this would be also non-standard model CP charged the Higgs mass scaled. And actually, I also need to cover the vacuum stability conditions as well as the one more condition, but due to lack of time, I passed that part. But the vacuum stability conditions is very stable due to the decoupling limit and something else. So if you are interested, I recommend you to refer to our papers. So there you can find some suitable information about vacuum stability conditions and something else. So here I will talk about the muon anomaly mounting moment with the scalar exchange. So as I told you, we have the 3 non-standard model scalar contributions. Participating in this muon G-2 mediated by the scalars. 2 of them are the CP even, and 1 of them is the CP odd. So we can define the from this effective Lagrangian, we can derive this analytic expression for the scalar exchange, muon G minus 2 with the scalar exchange. So, and then we want to cover this electroweak precision observables, which are the oblique parameters T, S, U, and this W mass anomaly, because the W mass anomaly can be explained in terms of this oblique parameters. So the first task is to write down each covariant derivative of each Higgs scalars. As I can see here, maybe you can build in some suitable quantum numbers from our model frame, and then maybe the gauge Lagrangian takes this form, and then from this gauge Lagrangian we can derive this gauge scaled mass matrix, and then from this one you can find some Chepra mass scaled condition from these 3 terms. So in that way we can define the gauge terms, and then one more preparation to investigate the oblique parameters is here. We relaxed the charge conservation, the electro charge conservation by expressing this charge Higgs in terms of 2 neutral scalars. So this is the charge Higgs, up-type charge Higgs, and this is down-type charge Higgs, and we want to express this charge Higgs in terms of 2 neutral scalars, as in the W gauge boson. And then we are ready to evaluate these oblique parameters. So here, in order to investigate these oblique parameters, we only have the neutral field in the interaction basis, and then we can investigate all these oblique parameters, and we will separate each oblique parameter by its standard model part and the new physics part, and we will isolate this new physics part to be fitted in the experimental page. And for the convenience, we call this new physics effect to be the delta T, S, U respectively. So let me start from this T parameter first. So T parameter takes the form of this one, and this phi, the capital phi, is the vacuum, the polarization amplitude consisting of the initial gauge boson 3, A mu 3, and the final gauge boson A mu 3. So maybe this is defined by the difference between 3 and 1 and I draw all the diagrams. So it starts from the 3 and 3 with 3, and also this is mediated by the fermions, the vectorlike fermion or the standard model fermions, and then similarly this is the charge some scalars and the other neutral scalars, and one scalar and one gauge boson. So this is 3. Similarly, I also draw all the possible polarized diagrams for the 1 the vacuum polarization amplitude 1 these are 1 and these are 3. So using after evaluating the diagrams, we can derive the standard model prediction to the T parameter. So which is which is bound by this one. And if you are interested in the new physics effect of this diagrams, I also encourage you to refer to our paper. There is all the derived new physics effect in our paper. So and this derived standard model T prediction is well consistent with the previous result. So and the experimental bound for the new physics contribution of T parameter at 1 sigma with this point. So our new physics the contribution should be located in this one. This is 1 sigma error. And similarly, I also calculate this S parameter, and the S parameter is simply from the 3 the vacuum polarization amplitude, the one of the external length, the outgoing external length should be replaced by the P mu, because this is 3, 0. So in that way, this is the same as this 3, but the outgoing this leg is replaced by this P mu. So the standard model contribution to the S parameter in the DSM model is like this way, where the C1 and the C2 take this numerical values, and its experimental bound for the new physics over the S parameter takes this value. Similarly, we also calculated this U parameter, and this U parameter takes exactly the same form of this one, but instead we need to differentiate this contribution of the 3 or 1. So therefore, I skip to put the same diagrams here, and derive the standard model contribution to the U parameter, and which is defined by this way, and the C and 3 and 4 has some this numerical values, and its experimental values text this here. And this W method anomaly is defined in this way. So if you take a look at this one, this is some coefficient, and is defined by the linear combination of the calculated the new physics vector of S, T, and U. And it's a Snell model prediction has this value, and this W method determined by the CDF collaboration gives this value, which has the 7 sigma Snell model deviations, so which is quite sizable at the moment. So theoretical W method derivation of equation, this one can be rewritten by subtracting from the experimental to this Snell model effect, and we found that our new physics contribution should be located in this one at 1 sigma constraint. So I will talk about our pre-parameter setup for this the oblique parameter as well as muon mass with scalar exchange. So here we set up this tangent beta is 50, and as I told you, which means this downtime Higgs becomes this numerical value of to be 5, which is very close to the big bang method. By doing so, we can also implement the second generation of a fermion method to be very close to unity, so which is a very preferred choice to explain muon mass. Because if this value is for example 10 or the other value, which means this B2 becomes much heavier than the 5, which becomes the Huchan constant related to muon mass with the scalar exchange will be much more suppressed. So which means which becomes much more difficult to explain muon mass. Therefore, this is a preferred choice in our SM model. So similarly, we also set some pre-parameter reason for the Huchan constant as well as the heavy vector-like method, which is actually same condition implemented in our previous charge response sector. This is a mass parameter, and this is the quantic coupling constant. And here we implemented the vacuum stability conditions as well as the decoupling limit. So you can see lambda 5 and 7, you can see some these questions which already showed in the decoupling limit, and 1, 2, 3 is the constrained by the vacuum stability conditions as well as. And here I also added this additional factors to find some correlation between these coupling constants. So here the conditions implemented, condition and constraint imposed here. So this is the same condition already implemented in the charge response sector simulation previous, and then all of the Huchan constant should be there in the perturbative limit in the entire fitting process. Whereas similarly, this quantic coupling constant should be this should be 4 pi, not the square root of 4 pi. This is a typo. It should be smaller than the 4 pi, and then also implemented the vacuum stability conditions as well as the coupling limit. So using the 1 plus minus kappa, I varied these parameters randomly. So using the random walk simulations, I try to converge it. I try to beat this chi-square values further, and use the chi-square values I defined this way. So here, what we did, beat is the Snell model Higgs method, and this deviations SWW and the R gamma gamma, and these are actually safe from because we are making using of the decoupling limit. So these are actually very close to their experimental value and unity. And so maybe we can further focus on the rest of the observers, which are muon mass with scalar exchange, T, S, U parameters, as well as the W mass anomaly. So this is a chi-square function, and then I will show you our result. So by fitting this chi-square function as much as possible, we were able to see that first of all, the oblique parameters are well within their experimental limit. So the x-axis tells the S parameter, and the y-axis tells the T parameter. Legend is one of them is U, and this is a W mass anomaly. And we found that all of our oblique parameters are within their experimental constant, and most up to 2 sigma over each experimental constraint. Whereas for the W mass anomaly, we also saw that the prediction is well within the 1 sigma constant, nearly 1 sigma constant over each one. And then I also investigated this mass ratio between the light CP1 Higgs H1 and this H2, and this is muon G-2. So as you can see here, our muon G-2 prediction runs from the 1.3 to 1.7, which is the 2 sigma region. So our muon G-2 prediction is also good. And here I just changed the order of the legend and this x-axis. And so here we found that mass of light CP even Higgs is very strongly proportional to the CP order scalars shows they are nearly proportional to 1 to 1. So similarly, I put the muon G-2. So this is the heavier one. This is actually the same range as appeared in here. And then I also investigated the other plots because there are the other parameters, but most of them are not very interesting because they show no correlations between each parameter error. But instead, I want to focus on this one only. So if you take a look at this one, the x-axis is the Z-prime mass, which is governed by the table of singlet lepton P3, and then this is muon G mass. So if this Z prime gets heavier, as you can see here, our muon G mass prediction gets much lower. So if this becomes much heavier, then we cannot beat the muon G mass 2 error. So this is the reason why I emphasize we can connect this Z prime method and the Z prime with the non-sum scalar via the scalar potential in the theoretically interesting Z prime regions. If we out of the theoretically Z prime regions by considering all the experimental constraints, actually we cannot connect this Z prime and the non-sum scalar error in the scalar potential under consideration. So I will conclude this talk. So here, main findings in this work are as follows. First of all, the first LK anomaly and the muon G mass cannot be explained simultaneously by the same new physics in a minimally extended Z prime model. Next, they can be connected in a specific reason, theoretically interesting Z prime reason via the scalar potential under consideration by fitting the muon G mass with the scalar exchange and oblique parameters TSU as well as double mass anomaly up to at most 1 or 2 sigma of their experimental constraints. Finally, the scanned vector-like fermion masses are not ruled out by the athletic experiments. So here I listed all the vector-like child reactions investigated in this model, and none of this vector-like fermion masses are not ruled out by the athletic experimental reason. And here the ones highlighted in blue means their masses are degenerated, which plays a very crucial role to explain the oblique parameters without violating the custodial symmetry or the other symmetries. Thank you very much for your attention. And if you have any questions, please feel free to ask me.
Huchan, thank you very much for the very comprehensive and very nice talk. Any question from the audience? Question from the audience?
Yeah, well, I continue to ask the question before because I understand the answer. Why is that there is no any condition coming from electron positron going to muon anti-muon? The C prime should contribute there, and maybe you can get some restrictions from that cross section. I mean, so I didn't understand your answer. Why is that not important?
Yes, let's go back to the topic. One of the initial pages. Just a moment.
No, it's completely general. I mean, you have electron positron going to muon anti-muon, the C prime should contribute. Why not?
Yes, right. But here, actually our starting point is this fully rotated meson matrix. So in this model, we cannot implement the electron mass. Therefore, we cannot have the access to the electron, the G minus. Actually, I think this is important, but as I emphasized at the beginning of this talk, here, I told that the electron G minus is the significance is reduced by from the minus 2.4 to 1.6. So I think phenomenologically, this electron G minus gets less important, definitely.
It's not related to G minus 2 of the electron. I mean, it's just, no, you haven't even considered G minus 2 of the electron. I mean, what's the C prime in that? You haven't considered that. So, well, okay, thank you very much, but I didn't follow you.
Yes. Next time, if possible, I try to supplement this idea by considering the electron G mass together. So in this work, we haven't considered the electron, the contribution to Z prime. But next time, yes, we can. I think it can be some potential research, including this Z prime to electron pairs.
Okay, thank you.
I would like to add a comment. In this math metric that Huchan grows in this basis where the first and second row of the charge lepton math metric which are vanishing, then in order to have the in general in order to have the C prime couplings to fermions, these C prime couplings to fermions arise only after the missing with the standard model charge fermions. And in the table of particle assignment, the standard model fermionic field, they had vanishing U1 prime charge, whereas the charge resulting, whereas the particles, the non-standard model fermionic particle, they have non-vanishing U1 prime charge. So the interaction of the C prime with the standard model fermion arises only through the missing with the heavy fermions. Here, given that the number of Sisson mediator for the case of standard model charge fermions is only 2 heavy Sisson mediator arising from the 4th family of the fermionic doublet and the 4th family of right-handed doublet. Then, when writing this, the mass metric in the basis, given that there is only one massless particle because only 2 Sisson mediator, when writing the charge lepton mass metric in the basis of equation 7, then there is no way to couple the C prime gauge boson to the first family of a standard model charge lepton, because there is no here there is no the missing to we don't have missing with the first family. However, the model can be extended, for example, either by adding one can add a fifth family, or another alternative could be to add let's say vector-like family, which will be the easier extension, char vector-like family. However, the char vector-like family singlet under the standard model gauge group should have the same U1 prime char. Then, in order to fill the entries, it may be the extension of the model would require to us an extra singlet scalar field with appropriate U1 prime char. In that way, the inclusion of this extra char vector-like family will generate a missing between the fifth family of left-handed lepton doublet or fifth family of right-handed standard model leptonic field with this heavy with this heavy fermion. Draw this missing, then the C prime will couple to the electron, and in that case, we will have the E plus E minus going to mu plus mu minus. In this current
Okay, thank you.
So this is for clarifying.
Okay,
More questions, comments? Professor Ivan, Marat, and any more questions? If not, there are questions?
no, thank you.
If there are no more questions, we send the speaker Huchan, and we meet in the next seminar.
Thank you very much, everyone, for your time, important time.
Many thanks. See you in the next seminar. Thanks a lot.
Thank you, Antonio.
Thanks, Huchan. See you.